Hello everybody and welcome to NPTEL online certification course which is brought on the SWAYAM portal, and from IIT Roorkee. The course is Semiconductor Devices for Next Generation Field Effect Transistors, a Physics Perspective. Short introduction of myself. I am the course instructor for this course and my name is Sudeb Dasgupta, and I am a professor in the Department of Electronics and Communication Engineering at IIT Roorkee. Now, let me go. The first part of the lecture will be more of an introduction to the course, the motivation why this course should be taken by learners, and also what are the possible outcomes of the course in the next 12 weeks which we will go ahead for this course. With this basic background, let me start the introduction to the course. So, this course is primarily used or will be used to build up your basic concepts right from MOS capacitors and up to the advanced topics, right, which primarily will be MOS capacitor will be more of a 2-terminal device, and then we move to 3-terminal device and finally to a 4-terminal device. And it will be useful for those who are pursuing a career in VLSI, right. Either you are in academia and you want to upskill yourself, or you are in industry and you want to gain more knowledge in this domain. So, this course will be primarily directed towards such a learner. Let me give you a brief prerequisite here. The prerequisite for this course is you should have a basic knowledge about the solid state physics, some basic idea, and also a basic idea on your mathematics, right. Basic mathematics you should have an idea on. What we will go as we move along is we will have an in-depth understanding of all the type of FETs available as of today, right. Now, the obvious reason why we are studying this is, if you look back at the International Technology Roadmap for Semiconductors, which is ITRS, right, you will see that in coming years, and by 2030, 2032, you will have devices or field effect transistor devices which are not only gate all around, but typically having absolutely different structures, right. So, as a learner you should be ready with the knowledge right from physics of the device to its fabrication and finally its assimilation into circuit analysis. And that is the reason this course would start with basic MOSFET, right, field effect transistor. Then we will move ahead and do a good amount of work on gate all around FETs, which is the gate is surrounding the channel, and we will see what are the various forms of GAA FET and how it can be useful for circuit simulation purposes. We will also look into negative capacitance FET, which is coming up in a big way in most of the device structures. Look at maybe one example of a high power FET, primarily used in automobile industry, primarily used in industries where the power requirements are very high, and then finally end up our course of this subject by looking at 2D material based FETs, right. So, this is the overall sort of a course structure which you will be actually going through in this device. Prerequisite, as I discussed with you, you should have a knowledge of the basic physics of the device, and second is you should have a knowledge of the basic mathematics of the device. This year is 2024-25, you will be actually going through this document. Your requirement for this devices are all for future technologies, typically around 27 to 28, 2027, 28, we will have these devices manufactured and fabricated. Not all of them, or most of them have been done, few of them are supposed to be fabricated, and technology oriented goals will be set up for these devices. So, that is the reason this course is sort of aligned in that domain, so that you have a strong foundation of cutting edge advancement in the areas of microelectronics and device physics. Now, let me give you what this course will try to do to you, right. I assume that you do have a knowledge of semiconductors, basic semiconductors. From there we will try to pick up and give you an idea about the basic concepts of VLSI, right from the device level. So, this subject is not more to do with circuit analysis, but more to do with basic device physics. And that is the reason you will see at the very onset of the program I told you it is a physics perspective which is important, right. And therefore, you will be actually given a very good background of physics for all the devices, right from its device physics to its IV characteristics and CV characteristics, which will help you to take that up in circuit analysis for later courses. What you will be acquiring skills for, you will be actually gaining hands on knowledge of the latest technologies, and we will do some hands on training on EDA tools. As far as this course is concerned, we will try to take up some basic EDA tools and its development as we move along. Where you will be stationed in terms of people who are working, you will be basically staying ahead of curve by learning these cutting edge technologies, and these are, to an extent, some of them are beyond CMOS technologies. So, all of you must be aware of that the CMOS is coming towards its logical ending. So, you should be in a position to position yourself in such a place such that you can take up, you understand the backside of it or the background of it, which is basically your FET technology, and you can also look at the future technologies which is basically on the beyond CMOS technology. So, this course will try to prepare you for that sort of a future stay ahead technologies, right. Okay. Let me therefore run through the course. A quick run through the course, week wise I will run through so that you know what you are expected to do in this course. This course is of 12 weeks, which is about 30 hours. There will be assignments at the end of each week, right. So, you will have assignments at the end of each week. Let me use a pen to showcase what I am trying to say. So, you will have to, it is basically a 12 weeks course, as I told you. This 12 weeks course will be divided into shorter lectures, smaller lectures of approximately half an hour, and the learner which is you in front of me can go ahead with their own pace. So, I would recommend that do not go through these PowerPoint presentations and videos at a very fast pace. You need to go back to the videos, come back, rewind your video and have a look into it once again, and we are always ready for answering any questions which you have. You can send me an email, or through YouTube you can send me a question, or through NPTEL. If there are live sessions, we will be able to take up those sessions as well. So, as I told you, there will be interactive live sessions for you, and this will be handled by my TA and the instructor, which is myself. There will be, of course, certification examinations which will be there, and these certification examinations in all probability will be sort of online examinations where multiple choice questions will be given, and you should be able to answer the questions properly, and a certification will be issued by NPTEL office stating that you have actually certified this course, you have passed this course, provided your course is above a certain benchmark value of marks, right. So, this is as far as certification examinations are concerned, and this happens at the end of the session. However, please keep in mind that one need not always appear for the examinations, right. You can as well just do the course just out of your interest, which means that you just do the course as you move along, and if you want to give an examination to get the certificate, please go ahead. If you are not interested to do that, then you can as well just do the course, understand the subject just for the learning purposes, right. The last point, it is always available on the NPTEL platform, right. So, it is available on the NPTEL platform, the whole course will be available on the NPTEL platform, and you can therefore, as I told to you, learn at your own pace, but the examination will be held after 30 hours, which is typically 12 weeks. Around after 3 months of registration, you will have these sessions. What we will be giving to you, the TAs and myself, we will give you assignments after each week, right. So, each week will typically have 5 lectures, and so each week we expect that there will be, so each week we will have approximately 5 lectures of 30 to 35 minutes each, right, and this will be followed by one assignment, right. This assignment will be there, right. So, this will be 5-week course, 1 week will have 5 lectures, 30 to 35 minutes plus assignment. This assignment will be not a very straightforward question, but will require your proper understanding of the lecture. And the advantage of it is, unlike offline classes, is in online classes you can always go back to the appropriate section in the video to answer a question if you have not understood at that point of time, right. So, that way it is very advantageous for the learner in this platform. As I discussed with you, it is always available on the NPTEL platform, and you can actually use this course for doing that, right. And I am also available on email. You can ask questions on email, the TA and I will be able to answer those questions. Let me go now week after week, the 12 weeks which we are supposed to do in this program. And the first week will be MOS capacitors, right. And the MOS capacitor is basically taking the metal. MOS basically means, and we will discuss this in detail, but at this stage even I can tell you, it is basically metal, right, oxide and then semiconductor. So, I have this into design, right. So, I have a metal, oxide, semiconductor, that consists of MOS. Those who are not initiated in this field, that is the reason it is known as MOS. We will study what is a MOS, right, what is a MOS, what is the structure of a MOS. Then we will introduce to you MOS using energy band diagrams, and then look into the second order effects in MOS capacitors, and then CV of a MOS capacitor. CV means capacitance versus voltage characteristics of MOS. CV means capacitance, and V effectively means voltage. So, if you apply a voltage on a MOS capacitor, then how does the capacitor vary with varying values of voltage on a MOS capacitor is what we study. You will ask me why this study is important, why this week is important. This week is important because in this week you will be learning about MOS capacitor. All your current IC design where you use capacitors, you do not use passive capacitors in most of the places, you use a MOS capacitor, right. And therefore, understanding its capacitance value variations with the applied biases is a very important task as a designer in a sense. So, that is the reason this week 1 is important. Here I will give you a basic idea about energy band diagram, which possibly you must have studied in a solid state course or in a basic electronics course, sort of a 101 course in your college or in your industry, wherever you are doing it. And I will take it from there onwards to explain to you how a MOS capacitor is basically working in a sense, right. So, this is week 1 which I wanted to showcase to you as far as this course is concerned. And this will be stationed where? This will be the first time where you will be actually learning the MOS capacitor as a active device. From active device I am going to generate a MOS device, and from there how will you take it forward towards designing a MOS cap, that will be done in week 1. Let me come to week 2. Week 2 we come, and because I am going a bit early in this case as compared to conventional device courses, we will be not only restricting ourselves to MOS and MOSFET, we will be going further than this, right. And that is the reason, as you can see in week 2, which will be again 2.5 hours, will be on MOSFETs and its application, basic application as a switch and an amplifier. So, I will introduce to you MOSFET, and this MOSFET is basically a FET device. As you can see, this is metal oxide semiconductor field effect transistor, and we will be introducing the MOS capacitor. We will be looking into current versus voltage analysis and capacitance versus voltage characteristics of MOSFET, right. Why is it important? Because MOSFET happens to be the workhorse of any VLSI industry as of today, be it in the analog domain or in the digital domain. All of the active devices are basically MOS based devices, all are MOSFETs, and therefore, its operation with applied biases will be very important, so that a priori you can predict what is the value of current and capacitance when a particular bias is applied to a MOSFET, right. FET means this is a field effect transistor, right. We will discuss all these things in detail as we go week by week. Now, another important topic of interest to many of you will be capacitance modeling for high frequency and low frequency. So, this is your high frequency modeling, this is high frequency, and this is your low frequency. So, this will be used, and you will ask me where is it important? It is important from the sense that when you operate your circuits at low frequency, right, how does the capacitance behave, right, and how does it influence the output characteristics of a circuit, and when it works in high frequency domain, how does it behave. That is what we will be doing in class number 3 of week number 2. Now, once we have done that, the capacitance modeling, we will integrate that with the bulk MOSFET and try to do what is shown in class 4, which is basically a high frequency and a low frequency modeling on bulk MOSFETs. And these are all bulk MOSFETs, mind you. We are not at all going to any exotic MOSFET. These are bulk MOSFETs, the traditional MOSFETs which you have studied in your devices course. Finally, in class number 5, we will take MOSFET as a switch and an amplifier. So, these are the application domain which I was talking about. So, this is the application domain, and we will try to give you an idea about how I can use MOSFET for an amplifier, right. So, this is your analog domain mode of. So, this is your analog domain, right, and the first one is more of a sort of a digital domain, I can say, right. So, I have a digital domain here. So, this class will showcase to you that the MOSFET is such a vibrant and a easy device that you can actually plug and place it both in analog as well as digital for getting the output characteristics. So, this we will do it. Let me come to class number 3, right, or week 3 maybe, and this is basically my MOSFET SPICE models. Why this week was added and it is not there in many of the courses. The reason being that the first EDA tool which you encounter typically in circuit simulation is SPICE, right. It can be an LT SPICE, it can be H SPICE, it can be T SPICE, P SPICE. There are many versions of SPICE. SPICE is a EDA tool, a very basic EDA tool to discuss with you the current characteristics, how the behavior of current versus voltage is there, and so on and so forth. So, what we will do, and therefore, you should be aware that in a MOSFET how does the SPICE model fits, right. So, that you can actually manipulate it in a proper fashion in order to discuss the various MOSFET models, right, SPICE models in MOSFET, right. There are various levels of SPICE. As the level goes on increasing, the accuracy becomes better and better. However, the time taken for it to converge to a set of values will be also very large, right. So, this week is primarily dedicated to the EDA tool of SPICE here. We will do introduction to MOSFET SPICE model, we will discuss SPICE model equations. We will also look into the SPICE model for mass transistors, right, and then we will look into diode model, and then some simulation techniques I will showcase with you in terms of actual SPICE model equations, right. So, that this will be done in this week number 3. Let me come to week number 4 now. So, this is week number 4, right. So, week number 4 is slight deviation from the exact nature of the whole course. This is basically heterostructure, which basically means that we will be looking into structures which are sort of sandwich structures, right. It is not only two material, there may be multiple materials sandwiched with respect to each other, and therefore, we will study its various properties in terms of carrier and transport of the devices, which means that in a heterostructure, if we apply a bias, how does the carrier move from point A to point B will be actually discussed in this class number 2. Of course, to do that, in fact, you need to learn about the band diagram of heterostructure. So, how the band diagram of heterostructure is placed will be discussed in class number 3, right. As an example of that, we will discuss with you a PN junction heterostructure diode, and then finally, in class number 5, we will discuss about the properties and applications of semiconductor heterostructure, right. Till we come to week 4, I would request you all to have a very good understanding of energy band diagram, right. So, I would request all of you that if you before chapter 4 or maybe say week 4, right, have a understanding of this thing, energy band diagrams. This is quite important, right. Please keep this in your mind while you are while you are studying this course, right, will be very, very useful for you, right. All right. Let me come to week 5 now. Week 5 comes to short channel effect. Now, what is the short channel effect? We will come to that later on, but what we will do is that till now we will be dealing with MOSFETs which are long channel of the order of few micron or maybe 1 micron, 180 nanometer or more than that, right. But as you are aware, we are actually reducing the dimensions of the devices, and when you reduce the dimension of the device, all second order effects comes into picture. So, we will be doing basically all the second order effects such as DIBL, drain induced barrier lowering, gate induced drain leakage, GIDL, and subthreshold swings. So, subthreshold swing we will also look into the fact. We will also look into mobility and scattering effects in short channel effects, and another important point which is class 4 we are dealing with the velocity saturation effects, which basically means that if you actually start to reduce the dimension of the device, the electric field is very large, and therefore, the velocity gained by the charge carriers are so high that beyond the point the velocity does not increase, it saturates to a level. When the velocity saturates, the current tends to saturate. So, that we will study in a short channel effect. Such effects are not visible for long channel, right, they are only visible for short channel devices, and the reason being very simple, the electric field is pretty high in short channel devices, which results in a higher velocity of the charge carriers. Now, while velocity saturation effects are important, because of high velocity of the charge carriers, you will have something known as hot carrier effect, right, and there will be self heating effect in a device. This will be quite important and interesting for later weeks to come inside, because the self heating effect we will be dealing at many other places as we move along in the various weeks of the course. Let me come to week number 6 now and show to you what we will do. This is where we break up from conventional single gate bulk MOSFET to a double gate bulk MOSFET, right, and we introduce to you a double gate MOSFET. I will explain to you what is a SOI MOSFET, silicon on insulator MOSFET. We will also look into partially and fully depleted MOSFET, which is PD and FD MOSFET. This is also referred to as PD. This is also referred to as PD, partially depleted, and this is FD, which is fully depleted MOSFET. Then we will take up these devices and check its subthreshold swing and transconductance, right. What is a transconductance? Transconductance is basically the rate of change of current with gate voltage, right. Just to give you an information at this place, this what we will refer to as a transconductance GM, right, and we will also look into subthreshold swings. So, why it is important from double gate MOSFET? I need to compare that with a bulk MOSFET and show to you that this has had a better transconductance and subthreshold swing as compared to a single gate MOSFET, and therefore, its utility for fast switching action and high amplification will be quite interesting, and that is the reason class 4 of this week is quite interesting and important. Class 4 comes to small and large signal modeling. Here we will do what? We will see what is the input signal, and depending upon the amplitude of the input signal, we will see some modifications in the overall modeling, that we will do in the class number 4. In class 5th class or the last class of week 6, we will look into junctionless transistor, which is again an upcoming emerging device, already done, quite a work has already been done in MOSFET, but I will try to explain to you with the background of FD, PD and bulk MOSFET with you. Let me come to week number 7 now. This is quite interesting, though it requires much more of understanding, but a new device has been actually generated way back in 2005-6 when FinFET was introduced, right. The concept of FinFET was introduced. So, week number 7 deals with FinFET, right, and this is a successor to MOSFET. All your current technology, low technology nodes are all FinFET based. So, you should know classically how does a FinFET look like in terms of structure. It is quite different from MOSFET. MOSFET is a planar structure, FinFET is sort of a quasi planar structure, right. So, that is the reason if you see class 2, we are looking into the structural classification of FinFET, which means look at FinFET and you can tell me after this class on what structure the FinFET is based, right. This will be doing in class number 2. Class number 3 we will be looking into the RLC FinFET modeling. RLC means resistance, inductance, capacitance modeling. You will ask me why this is important. This is important because you need to extract the FinFET's capacitance, parasitic capacitances, parasitic resistances and inductances, so that you can predict its frequency of operation when you are doing a AC frequency or even when you are doing a transient analysis. For DC analysis, of course, they do not make any sense, but for transient analysis they are very important, and therefore this FinFET modeling will be used more so in transient and AC analysis, right. We will then finally go to class number 4, which is high frequency or small signal modeling, and class number 5 will be a new topic where we will take a FinFET from device and then extend up to a circuit. So, let us take a FinFET, optimize it, and then take the optimized FinFET and try to put into a circuit design. What can be a circuit design? Let us simple NAND, two input NAND gate or 2 input NOR gate, right. That will be class number 5 as far as FinFET is concerned. Okay. Week number 8, this is where we shift gears, right. Till now was the conventional which has been taught to you in your most of your BTech, if not week number 7, but till week number 6 most of the institutes do cover that part till week number 6, but post week number 6 you will see we will shift gears and it will be slightly on the higher level of understanding. So, I would request all of you by week number 6 make yourself sort of absolutely clear about what the concepts are, so that from when you start from week number 7, 8 and onwards your concepts are clear and you can introduce them to new devices as it comes along. Week number 8 comes with with various types of GAA structure, right, which means that if I have a GAA structure which is gate, the GAA basically means gate all around, right. This is gate all around. So, I have a gate all around structure. I will explain to you what these gate all around structures are, and then we will look into nanosheet FETs, right. This is coming up in a big way, and by 2027-28 we would actually see its maturity levels going very high. We will look into the process variations in nanosheet FET, and as an example of nanosheet FET we will take up an analog perspective of nanosheet FET, right. We will see how an analog performance happens in nanosheet FET. Let me come to week number 9, again a new topic and not taught in any of the bachelor UG courses or even PG courses, and this is what is known as a Fox sheet FET and a CFET. Fox sheet FET and complementary FET, right. These are all sub 3 nanometer node technologies which we are looking into, right, and we will look into discuss the challenges and importance of Fox sheet with respect to nanosheet and bulk MOSFET. We will also look into CFET, look into its advancement and how industry is adopting the CFET, look at its device physics, and very important in CFET the structural differences with Fox sheet FETs or even nanosheet FETs, that we need to bring in class number 3. We will maybe take up a design issue in CFET as far as CFET is concerned in class number 4, and finally can we optimize CFET for semiconductor scaling, right. These classes will be typically of the order of one for 30 minutes or 35 minutes, right. Each one of them will be of 30 and 35 minutes. The books which I will refer to I will tell you as we move along, but this is what the course structure will be typically looking at. Let me come to week number 10, and this is slightly different from conceptually, the physics wise slightly different from what you have studied till now, right. This is basically a negative capacitance FET, and for the first time you will see the concept of negative capacitance, and hence the class 1 is basically a concept note of negative capacitance, right, and you should be able to look into the negative capacitance from the point of view its advantages and disadvantages. To extend negative capacitance we will looking into ferrofets and ferrofet based memory design, right. So, we will take up a ferrofet, I will explain to you what these are as we move along in class 2, and then take a ferrofet and put it in a memory and see how a memory can actually work as a memory can actually be efficient memory in a sense. Finally, we will be looking at the advantages and challenges of NCFET, and we will do some amount of basic modeling of NCFET, right. Now, this modeling of NCFET will start with basic Poisson equation and we will see how to move along with, but modeling will be basically an analytical modeling. So, this will be more of an analytical modeling rather than anything else, right. analytical modeling. And finally, as a precursor to week 11, we will state the phase transition material based design. Let me come to week 11, and this is basically a 3-5 semiconductor, a very important part as far as this course is concerned. However, since my thrust was only on the FET device, so on the silicon FET device per se, so my 3-5 semiconductor takes only 1 week out of the total 12 weeks, where I introduce to you the 3-5 materials. Typically where they are used, typically they are used at high power and high speed devices. One of the major 3-5 is HEMT, high electron mobility transistor. We will look into its modeling and simulation, and then look into 3-5 semiconductor FET, right. So we have looked into silicon FET, and then we will look into 3-5 semiconductor FET, and finally we will do an application of 3-5 semiconductor FET for circuit applications. So this week does not follow the traditional silicon one, but goes for a traditional 3-5 material, for example gallium arsenide or gallium intermanide phosphide and so on and so forth, and gives you an idea how is it different from silicon FET and how is it important from silicon FET as compared to a silicon FET. Let me come to the last week of the course, and this is where we slightly give you an idea about the various upcoming materials used for FET. So I will tell you why this week is important. So there are 2 or 3 ways of looking into the device. So one is the structural variation in the device as the device moves forward in time domain, and that is the reason you see bulk MOSFET initially, then you have double gate, then you have FinFET, then you have nanosheet, Fogsheet, CFET and so on and so forth. However, there is another group of scientists, researchers, academicians in industry, people are working on the materials aspect of it, right. So let us not change the structure of the device, but let us change the material of the device itself, so that we can extract the best out of the material, and that is the reason we end the lecture series in week 12 by giving you a small insight into a 2D material. I know 2.5 hours is not enough for such a important and a huge topic, but I just wanted to introduce to you so that you are ready to take up courses on this either on NPTEL or from outside, or read through books and so on and so forth. So that is the reason week 12 has been added. This takes care of our week 12 weeks of studying. So let me finally come to the outcome which is supposed to be done. Outcome will be after you have finished 12 weeks, you will be sort of ready to take up domain or to take up knowledge domain in the area of semiconductor devices, and that too specifically on the FET devices. So we will learn, by the time you will be having the whole flow of FET devices available to you, and then you need to, if you want to go ahead, you need to upskill your domain expertise. That will be useful in industry as well as in academia. If you want to go for higher studies, say you want to do for master studies, you want to go for PhD, that will be, this course will also be helpful to place you in that domain. And from industry point of view, I think from week number 6, 7 onwards, it will be very useful for you in terms of upskilling your domain knowledge in the area of devices, and then finally you need to integrate this with the current knowledge base in order to enhance the knowledge system. So this is as far as a brief outcome or design is concerned. We will start the next course now. Thank you.